let's solve this linear recurrence here using generating functions. So the idea is that if we define our generating function g of x as the summation n larger or equal than 0 an x to the n, the idea is that we want to use this recurrence to find a g of x that satisfies this, and then use some type of coefficient extraction technique. So maybe rewrite this as other generating functions that we know how to deal with, which in our case is mostly, how do you say, the geometric series, and use that to be able to find closed forms for this. Now, we've seen how to solve this in other ways, but now we're going to see through generating functions. Generating functions will be able to solve all linear recurrences, and you're only going to need the geometric series. But one of the nice things also is that the generating function techniques can be used to solve other recurrences also. Although in those cases, it's not always the case that it's as easy, or that you can actually, it's not going to be like using geometric series. You'll have to use something else, and sometimes it won't have like an easy solution, or there won't be a closed solution, but you'll be able to use properties of G to study your recurrence. But getting back to this problem, so let's solve this. Okay, so let's find first a generating function for that. So again, our recurrence was a n plus 2 equal to 3an plus 1 minus 2an, with initial conditions a0 equal to 0 and a1 equal to 1. And of course, so we had defined the generating function for this, or we had denoted it by this over here. And so this is what we are interested in. So the idea here is we want to obtain it from this recursion here. So how can we do that? Well, if we multiply both sides by x to the n plus 2 and take a summation, what we get is the following. So we'll get summation of an plus 2 x to the n plus 2, here from n larger or equal to 0, equal to 3 times the summation equal to 0 an plus 1 x to the n plus 2 minus 2 times summation n larger or equal than 0 an x to the n plus 2. Okay, so how can we do this? So what are the issues here? So we want to get this here somehow. So for this first term, the issue is that we would like this to be an n, right? But this summation is essentially starting at 2. So how we're going to solve that is we're essentially going to write that as the thing we're interested in. So this is just summation of an xn n larger or equal than 0. But notice that this summation here starts at 2, and this one starts at 0, so we just need to subtract the first 2 terms. Okay, so that takes care of this part. So for this part here, we have the similar issue that also things are not starting at n, but more than that, we also have this problem that these things are not matched to each other. Now, how can we solve that? Well, this x to the n plus 2 here, we can factor out an x, and then it would be x to the n plus 1. So we can write this as 3x summation n larger or equal than 0 n plus 1 x to the n plus 1. And the same for this one, but now there's a 2 difference here, so factor out an x squared minus 2x squared summation n larger or equal than 0 an x to the n. Okay, so now this one is actually good, this one is good, but this one here, it's just sort of like what we had here. We need to, it starts at 1 instead of starting at 0, so we can write it as this minus the one starting at 1. So let me just say that this part over here is the summation of an, so n starting at 0 here, x to the n, minus the first part, right? Because it doesn't have, so when this is 0, it starts at 1, so you just need to remove the 0 part, minus a0. And so what this means now is that we can replace this g of x here, here, and here, and we're going to get a function in terms of g of x. So like an equation in terms of g of x. So we're going to get g of x minus a0 minus a1x is equal to 3x g of x minus a0 minus 2x squared g of x, right? And so we can now use our initial conditions, a0 equal to 0, a1 equal to 1, to replace them here, here, and here. And when we do that, we obtain g of x minus 0 minus 1 here, so minus x is equal to 3x g of x minus 0, so just g of x, minus 2x squared g of x. And now you just need to solve this for g of x. So isolate the g of x, throw everything to the other side, and what you will obtain is that g of x is equal to x over 1 minus 3x plus 2x squared. So with this, we found the generating function for our sequence. So the sequence, the sequence given by this recursion here with these initial conditions has this generating function over here. And now we would like to use that to try to solve this. And the idea is that we would like to break this generating function into functions that we know generating, like that we know closed forms of. And in this case here, for linear recursions, you're always going to be able to break it into things that have the geometric series. So let's see how we do that. So the idea is that this is the function that we have, and we want to do partial fraction decomposition. So the first thing that we need to do is we need to solve or factor the denominator. And so we need to go and solve that. And if you go and either by finding its solutions or factoring or however you want, you'll be able to show that the bottom can be factored as 1 minus x, 1 minus 2x. So of course you could multiply this out and just check that you get exactly this. But yeah, but you need to know how to factor things. Again, these are the roots of the equation also. So yeah, go over that again and practice that a lot. So once we've done that, the idea with partial fraction decomposition is that we can rewrite this in the form a over 1 minus x plus b over 1 minus 2x. And so how do we find the way to do so? We multiply by this on both sides here. And so if we do that, we're going to get, so we will get x. So if you multiply, of course, if you multiply by 1 minus x, 1 minus 2x here, you just get x. Now when you multiply it here, the 1 minus x cancels out with this 1 minus x, and so you get a times 1 minus 2x plus b, and then the b, the 1 minus 2x cancel out, and you get b 1 minus x. And you can write this out, and matching coefficients, you need to essentially, so let's write it out. So if you do that, you will get a minus 2ax plus b minus bx. And so if you write this in, like, you match the coefficients here, so you get a plus b as the constant coefficient, and for the x here you get plus, let's say, minus 2a minus b times x. This polynomial here is equal to this polynomial here, which means that the coefficients need to match. So this polynomial here, the constant coefficient is 0, so the a plus b has to be equal to 0. And the coefficient of x, here it's 1, here it's minus 2a minus b, so this will be 1. So minus 2a minus b equal to 1. And so we need to solve this system here. Solving this system, we get a equal to minus 1 and b equal to 1. And so that tells us that our generating function can be written as 1 over 1 minus 2x minus 1 over 1 minus x. And so with this, we're going to be able to use now the geometric series, right? Because we do know the closed form for that. So now that we have this over here, we use the geometric series. So in this case, the 1 over 1 minus 2x, or just so we can remember the geometric series. So the geometric series said that 1 minus our x was summation n larger or equal than 0, r to the n, x to the n. So this first one is going to be summation n larger or equal than 0. So the first one is going to be, the r is 2, so this will be 2 to the n. And then the second one, the r is 1, so this is just going to be 2 to the n minus 1 to the n, which is just 1, x to the n. And so this means that our an, and remember j of x was summation of an x to the n larger or equal than 0. Thus, our sequence an is going to have the closed form 2 to the n minus 1. So just to recap, essentially, we wanted to solve this. We wanted to find a closed form for this, which, I mean, now we have. It's just given by 2 to the n minus 1. And what was the idea? Well, the idea to do that with generating functions is that you define a generating function for it, and now the recursion, you multiply on both sides by some power of x and take summations, and then you do algebra so that you get an equation in terms of your generating function and you solve for that. And so you're going to get this. And for linear recursions, you're always going to get something that's like a rational equation, so like a polynomial divided by some polynomial. And so what you will want to do is partial fraction decomposition. So you're going to have to sort of factor the polynomial in the bottom and then do the partial fraction decomposition. When you do that, you're essentially going to be able to write your generating function as sort of a combination of geometric series. And so then you just replace by the geometric series and you get your closed form.